Welcome to Episode 2. In this episode, we will talk about untrusted input. This is one of the most important ideas in Java secure coding. A lot of security problems start with a simple mistake. The program receives data from outside. Then it treats that data as if it were safe internal data. That is dangerous. External data can come from many places. It can come from HTTP requests, forms, cookies, headers, files, databases, APIs, environment variables, or messages. The key point is this. If the data can be influenced outside your trusted code, you should not trust it automatically. Before using it, the program should validate it, normalize it, and constrain it. That is the core idea of this episode. Why does this episode matter? Most security bugs begin when data crosses a trust boundary. A trust boundary is the line between trusted code and untrusted data. For example, your server code may be trusted, but a request parameter from a browser is not trusted. A file uploaded by a user is not trusted. A value received from another service may also be untrusted. The mistake is often small. A developer reads a value and uses it immediately. The code may work during normal testing, but attackers do not use the program in normal ways. They try unexpected values. They try long strings. They try special characters. They try values that change the meaning of SQL, XML, commands, logs, or paths. That is why input validation is a security habit, not just a data formatting habit. The rule focus in this episode is IDS. IDS means input validation and data sanitization. The goal is to prevent predictable Java coding errors before they become vulnerabilities. When you see an IDS rule, think about data flow. Where does the value come from? Can a user control it? Does it cross a trust boundary? Where is it used? Does it reach a dangerous operation? A dangerous operation is sometimes called a sink. Examples include SQL queries, XML parsers, command execution, file paths, logs, templates, and deserialization. The title of the rule gives you the topic, but the code examples show the real lesson. In this episode, we will focus on a simple review habit. Never treat external data as safe until the code proves it is safe. Let's compare the risky pattern and the safer pattern. In the risky code, the program reads the role parameter from the request. Then it checks whether the role equals admin. If the value is admin, the program shows the admin page. This looks simple, but it has a serious problem. The role comes from the request. That means the user may be able to change it. If the program trusts that value directly, a user may send role equals admin and reach a page they should not access. The safer pattern checks the role against allowed roles. If the role is allowed, the program shows the correct page. If not, it rejects the request. The safer version does not trust the input. It constrains the value before using it. This slide shows how an input bug becomes a security problem. Step 1. External input enters the program. This input may look harmless. Step 2. The program performs no validation. This is where the hidden assumption appears. The code assumes the value is safe. Step 3. The value reaches a dangerous sink. For example, it may reach SQL, XML, a command line, a file path, a log, or a template. Step 4. Unexpected behavior happens. The program may give access to the wrong user. It may run the wrong command. It may expose data. It may corrupt logs. Step 5. Validate first. The fix is not to guess what attackers might do. The fix is to define what valid input looks like and reject everything else. During code review, look for risk signals. The first risk signal is external data being used like internal data. For example, request parameters, headers, cookies, uploaded files, and API responses should not be trusted automatically. The second risk signal is a hidden assumption. The code treats a value as safe, but there is no visible safety step. The third risk signal is a dangerous operation happening before validation. For example, building a query, opening a file, writing to a log, or selecting a role. Now look for safer signals. Validation should be visible. The expected format should be clear. The allowed values should be defined. The unsafe path should reject the request. Good secure code makes the safe decision easy to see. Here is the developer checklist for untrusted input. First, ask where the value comes from. Can a user, another service, a file, or the environment influence it? Second, define the expected format, length, range, and encoding. For example, a role may only be user, manager, or admin. An ID may only be digits. A file name may not contain path traversal characters. Third, ask where the value goes. Does it reach SQL, XML, command execution, logs, files, or templates? The more dangerous the sync is, the stricter the validation should be. Fourth, prefer allow lists. Do not try to block every dangerous string. Define what is allowed and reject everything else. This is easier to review and safer in practice. Let's look at common mistakes. The first mistake is adding comments instead of changing behavior. A comment that says, "This input is checked by the client," is not enough. Client-side checks can be bypassed. The server must still validate the input. The second mistake is catching broad exceptions and continuing. If validation fails, the program should not continue with unsafe assumptions. The third mistake is trusting tests too much. Tests are useful, but attackers can try more cases than your test suite. The fourth mistake is using a generic fix. For example, escaping for HTML does not make a value safe for SQL. SQL, XML, file paths, logs, and commands all need different defenses. The context decides the correct protection. Here is the one-sentence idea for this episode. Untrusted input means secure Java code removes hidden assumptions and makes the safe path explicit. This sentence is simple but very powerful. Do not ask, "Is this value probably safe?" Ask, "Where does this value come from, and what proves it is safe?" If the code cannot answer that question, the code is relying on trust. Secure coding should not rely on trust. It should rely on validation, constraints, and explicit decisions. This is why input validation is at the center of Java secure coding. Many later topics connect back to this idea. SQL injection, command injection, XML injection, unsafe logging, file path bugs, and deserialization risks all start with untrusted data. Let's summarize episode 2. First, the most important question is this: can this value be influenced outside our code? If the answer is yes, treat the value as untrusted. Second, validate before the value reaches a dangerous operation. Do not wait until after the SQL query. Do not wait until after the file is opened. Do not wait until after the command is built. Third, use a rule-based mindset. Think in 4 parts: source, trust boundary, sync, and safe transformation. The source is where the data comes from. The trust boundary is where it enters your system. The sync is where it can cause harm. The safe transformation is the validation or sanitization step. In the next episode, we will apply this idea to SQL injection.